recording and go back to the course. Well, good morning. Thank you for attending our class again. We talked about one-way slab last lecture, okay? And we will have homework on one-way slab, unfortunately, today, right after we finish the lecture. But we'll see the deadline, try to adjust that either on next Wednesday or next Monday. So we'll decide after the lecture, okay? And we'll finish all the one-way slab story today and a little bit maybe on Wednesday if we have to stretch it along, but pretty much we're done with shear and one-way slab. Now, I want to say for the second coming exam, one-way slab will definitely have one big problem in terms of like breakdown of filling blank calculations. So you really need to know how to solve it. And to help you, I will also upload a textbook example of one-way slab in case you didn't purchase the textbook, and you will find more detailed solutions there. Please compare that with the notes we published from last lecture and have a better understanding. Okay, and we also we upload some of the figures to help you to remember some of the information we're going to teach today. Okay, all right, so let's get back to it. Let me share my screen right now so you can see it. And today is lecture 18, and we're going to talk about one-way slab. Okay, one-way slab. So let me remove this. And let's do this. Okay, so lecture 18, one-way slab, one-way slab. All right, so a quick recall what we had done before, right? Quick recall what we have done before. So now recall we had a one-way slab like this, one-way slab like this, okay? And supposedly this is a support. No, I should draw in the 3D. So this is like a roller support right here, and then continue slab like that, and then looks like this, and there's a support going this way, right? So that is a one-way slab, and we have two direction of reinforcement we talk about. One is this flexure reinforcement that goes in this way, and oops, there's a temperature and shrinkage reinforcement going this way, temperature and shrinkage reinforcement going this way. Okay, so this is temp plus shrinkage, and this is flexure. Okay, this is a flexure. All right, so that's what we talked about before. And we also mentioned that you need to find the bending moment. You need to find the bending moment, right? This way, right? At here, at the support, and then calculate it, MU, right? And then design for the reinforcement, AS, right? That's what we showed from last lecture. Now, for simply supported beam, right? If you look at from the side view, it looks like a simply supported beam like this. Say I have distributed load essentially. And my maximum moment usually is right here in the middle span. Usually is right here in the middle span. Let me just use this color. Okay, that's where my maximum moment is at. And also that is my apply moment for design. Apply moment for design. Okay, all right. Okay, so that is the bending moment. That is the flexure bending moment. All right, okay. So this is when we start when we have a simply supported condition. Simply supported condition. Easiest you can ever get, right? You cannot get more complicated. Sorry, you cannot get more easier than this. This is the easiest you ever get, right? So to calculate this is very simple. You have omega u, and then your mu is omega u L squared, and L is a span length. Life is beautiful, right? Life is simple, right? So we can calculate the maximum moment in the middle, However, though, this is simply supported case, which is often not the case. Okay, often not the case we see in the construction side. So simply supported. Okay, so we're going to talk about continuous one-way slab. Okay, continuous one-way slab. So what does continuous mean? What does continuous mean, right? So normally when we say continuous, we mean that the slab is sitting on multiple support. The slab is sitting on multiple support, right? That means I have multiple beams underneath the slab, and usually they are casted together. So I have this beam sitting underneath it. I have this beam sitting underneath it. I have this beam sitting underneath it, and I have this beam sitting underneath it. Okay, and when I say they're cast in place, cast together integrally, right? Integrally, I mean you don't have this line here. What you truly have is this line right here, this line right here, this line right here. Means they're together. They're casted together. They're casted together. Okay. So now if I really want to simplify the drawing and what the structure looks like is I can show it. It looks just like this. So it's just like this. Okay. So that is the one-way slab. That is the one-way slab. All right. So now what we're going to do about this, what we're going to do about this, right, is that we have a distributed load, right, from the top. And when we're trying to find the moment, in the slab, then don't forget, this is the span direction. This is the span direction. When we talk about span length, one, this is the direction, not the other way around. The other way is transverse, right? We only provide temperature shrinkage, don't care that much. It's mainly for span direction, the flexure is what we care about. So we need a moment, right here. Let me draw a cut here. Okay, we need a moment right here in this section, right? And we need a moment right here in this section, right? And we need a moment right here, of course. So it should be in the middle, okay? Sorry, let me redraw it. Still, it's the one-way slab cross section, but it's at the support. So right here, right here, right here, right here. Okay, forgot this one here. This is easy. Sorry, shouldn't. Because this is in the middle of the support and middle of the support right here. Okay, these are the critical section we need to find moment. Now, for continuous beam like this, finding moment is not that easy, isn't it? Finding that moment is not easy. Okay, so what do we need to know to find moment? So we need to use the influence line concept. Use influence line concept. Okay, all right. Since today it's a little bit easy, so I'm gonna use a lot of questions to help us interact. All right. So I'll pick my next victim. Who's on my list right here? Steven. Steven, are you there?
Yep. How are you doing?
Hey, how are you, buddy? So I got a quick question for you, sir. So what do you know about influence line concept? Can you quickly tell me what you think is influence line? You know, definition of that. I know that. Have you guys covered it in previous courses? Not sure.
No, I'm not recalling anything on it right now.
Okay. So that might be something new to us, right? That's fine. Thank you very much. So influence line, right? Means if I have a structure like this, and I want to find out what is the moment at a particular section, right? What is the moment of this particular section? I need to have a influence line, which means the shape or profile of the deformation that I can use to find out the moment, right? So for instance, if I want to find out the moment, okay, this is a little bit hard. In the middle of this point here, okay, so in the middle of this span here, I simply have to do is break it into two parts, break it in the left and right, okay, remove this connection right here, okay, okay. Now at any cross section right here, if I make a cut, I will expose several things. Now, given this is a bending dominant structure, I will mainly expose shear, this is my shear, and bending moment. So M and V. These are what I expose. Because I want to find the influence line for moment, I will only remove the moment constraint. That means these two parts will still be connected, but instead this direct connection like this, they will become something like this. It will become a hinge. Okay, why hinge? Because if it becomes hinge, I still preserve the shear transfer mechanism, but I did not have the moment. transfer mechanism anyway. In other words, if I have a moment here, I don't have any moment here. I don't have any moment here. Okay, so I want to make it like a hinge. Why is that? Because I want to see if I want to find a moment at this section, right? What kind of influence line I have. So I break it down. My beam will bend like this, simply like this. Simply like this. Okay, my beam will bend like this. Okay, now if I have a distributed load like this, okay, to find moment at this one here, let's call it point B. So let's call it MB, and this is omega U. Okay, all I have to do is find the values corresponding to all this loading, right? These value here. So let's call it influence line. So I call it IN influence line, INX. It's just a value, right? Let me use a red so you know which was what. Oops, here. So red, okay. So these red values are the influence values. Then this is called INX. How to get this, right? How to get this is you bend, this is 1, theta equal to 1, angle equal to 1. 1 what? 1 radian. 1 radian. And you get some value, and this is called influence line. Okay? So the moment MB would equal to a omega U distribution as a function of X, which is this is X, and dot product means multiply together and then add up again, which means INX and DX. Okay, this means that is how we get a moment. All right, I am pretty sure a lot of you guys are scared right now and scared, really bad and feel like, wow, what's this? And you didn't give us enough information. Are you counting us to do this? All the one-way slab continuous support? The answer is no. Don't worry about it, okay? Don't worry. This is more advanced topic. If you haven't noticed this, haven't learned this, don't worry. You learn this in grad school or later in your structure design life, okay? That's fine. All right. But this is not what we're really here for. What we're really here for is to observe that if I have moment on, let's name this A, B, C, sorry, I should call it A, B, prime, C, D, E. These are my structure support, okay? And B is the section. If I want to have a maximum bending moment at section here and center of the span, B prime C, at this point here, I have loading in this way, right? Which means it will give you moment, And I keep going and I say, now if I add this way, okay, I will also add more moment at B. Now, why I did not load my B prime C and DE is because you see the influence line, they're in a negative direction. Okay? They're in a negative direction. So if I put any positive loading here, because they're negative, and this is integration, that means I reduce the moment at point B here. So I do not want to load adjacent span DE because I want to see what is the maximum moment, positive bending, maximum moment at, negative bending at this point here at B. Okay, at B. All right, so the whole concept of drawing all this to tell you that we need pattern loading. We need patterned loading to achieve. We need a pattern loading to achieve maximum bending moment or maximum moment service load, more in general, right? In structure, in one-way slab, in one-way continuous slab. Okay, that's, oh shoot, sorry, continuous slab. That's the take-home message, right? Take-home message is we need pattern loading. All right, and this is very complicated to do on site, and sometimes mistakes happen. So ACI says, you know what? Let's do a simplified version. We will like simplified version. Okay, so here ACI said we need to say there are pattern loading. Okay, and don't forget the reason why we do pattern or pattern loading is to find maximum moment. We'll find the maximum moment so we can design for it. We can design for it. Okay, so ACI, use red, ACI 318, ACI 318, okay, 8.11.2, it defines loading patterns, right? To tell you the loading patterns you need to use. So you don't have to worry about the calculation. You just need to know which bay need to be loaded to determine the maximum design moment. Maximum design moment. Okay. And also shear. Okay. In continuous beams and one-way slab. In continuous beams or continuous one-way slab. Okay. So that means there are two scenarios. Right? Scenario number one is factor dead load, O dead load, right? On all spans. Okay, on all spans. All right, and factored plus factored live load on two adjacent spans. And that's it. Okay, what it looks like this. So if I have a beam, and let's just continue using our previous example. So I have 1, 2, 3, 4, 5, 5 support, right? To make it even more structurally sound, let me put them all in roller here, because we all need only one horizontal constraint to make it determinate. Okay, in this case, right, it's a dead load on all spans. So all the dead load, all the self weight, right, all the self weight need to be on all spans. So there's no exception. Load it all up, right? You load them all. It's called all spans, right? So here, load them all, and this is A, B, C, D, E, right? Load them all, and then factor live load, right? This is factor dead load, so this is 1.2 omega D, right? And then factor live load on two adjacent spans and no other. Two adjacent spans, right? No other. So what do you mean two adjacent spans, right? So let's take a look, right? Take two adjacent spans. So two adjacent spans here. There's one, right? There's a one, and there's a one. Okay, so if we're talking about support here, it's red. If I support here, right? And that is how we use, right? Two adjacent span, no others. Two adjacent span, no others. Okay, so scenario number two, factor dead load. Okay, dead load on all spans. So you have to consider both scenarios, okay? Both scenarios. And factored, okay? Factored live load on alternative, right? Alternate spans. Alternate spans. That means, right, I will have the same structure repeated here. Let me just copy it. Save me the time. Same structure, copy it, and then paste it here. Right, the dead load still all loaded, right? Dead load still all loaded. Okay, it's the live load that changes a little bit. So I don't have to worry about adjacent. I have to do alternative, right? Like this. Okay. All right, so that is to say this is 1.6 live, omega LL, and this is 1.6 live, and this is 1.6 live. Okay, that says you need to consider both scenarios to calculate a moment diagram, shear diagram, then find out the maximum. Okay, and then supposedly when you see a one-way slab like this all the way back here, right? You got to play is, you know, dead load right here. So this is dead, and this is 1.2, and I have to put the live somewhere here first. Calculate the moment diagram, right? And this is 1.6 live. And then you say, oh, alternatively, I have to put live load here and calculate here, right? So it's all a lot of messy stuff, right? You need to calculate a lot, right? A lot of moment diagram, a lot of shear diagram, too much. Don't want to do it. Don't want to do it. So ACI said, you know what? Let me make it even simpler, right? Even simpler for you. All right. Set. Then ACI says approximate analysis, right? It doesn't even have to have, you don't have to have calculate. You don't have to have them calculate out. You can just use ACI moment coefficient. ACI moment coefficient. Okay. ACI moment coefficients. So what is ACI moment coefficients, right? What is the moment coefficients, all right? Before we do that, right, let me share screen and take a look at it, right? And this is on your textbook, supposedly. Let me share my screen here. Can you guys see it? Can you guys see it?
I'm on it.
Oh, yeah, now Siri, you, but
okay. I found this on the web for moment coefficients.
Sure.
Moment coefficient?
All right.
Yep,
You
I
can
see
shut
it.
up now. Okay. Thank you, guys. Seems like I have a problem with my Siri. Okay, good. So you guys can see it, right? This is the table from ACI. Okay. Now I scratch here because you can find it in table 6-5-2, right? In ACI, supposedly, but these are the coefficients. These are the coefficients. So what does it mean is this is omega u is the live load and dead load factored, live load and dead load factored, and Ln is the span. Ln is the span. Okay, so it has all these requirements, right, to show you how to apply them, Okay. All right, so this is a little bit complicated, but I just want to show you this is what it looks like. So you don't have to remember it. All you have to do is know where to find it and know which one to pick. Okay, so I'll upload this, but I just want to show you what it looks like. So it just a factor, a number, multiply in front of the load, apply omega u, and this is span length Ln, okay? And I'll explain what it looks like in the figures, okay? So let me stop sharing and go back to my drawings, and let's see, right? Let's see. Okay, so, all right, so you see from that table, right? The table basically tells you that, I have so many different conditions. Say if I have n spans, and I have, say, if I'm talking about positive bending moment, right? And if it's n spans at the end, blah, blah, and you have some number which is 1/11. I'm using red so you can see it better. 1/11, some number multiplied by omega u Ln squared. And you can find this from table 652. Okay, I'll upload this one. For you. Okay, so this is the applied load, means omega u equal to 1.2 dead plus 1.6 live. Okay, and the Ln is essentially, can you guys see here? Ln is the clear span length. Okay, so how to use it? Right? How to use it? This is how to use it. Essentially, when I have a span, I'm just gonna draw it out. You can see it. Okay, I'm gonna draw the section out. For example, this is my slab on a beam, and I have 4 support. Okay, 4 support. Okay. Okay, slab on a beam for support. All right, and then I have the span, right? I have the span. So give you some dimension. Say the beam has a width. Let me just walk you through example straight. So beam has a width of 12 inch. Okay, and I have a distance between the span. So this is 13 feet, and this is from center to center 15 feet from center to center. What do we got here? 13 feet. Okay, and the height of the slab, let me use black, height of slab HF here equal to 6 inches. Okay, and total height of the beam, including the slab, let's say this is 22 inches with a depth of 19.5 inch. Depth of 19.5 inch. And you notice that this is square, right? This is square, and we call this prismatic. Okay, and I explain to why later why you need this. Okay, so this is essentially the geometry, right? And my point is, right, what I'm trying to do is I want to find the moment coefficient ACI. So find moment coefficient from ACI. Okay, and for the following slab, right, F prime C, let me use back. My color is a little bit changed different today. So F prime C is 4 KSI, okay, and yield strength bar is 60 KSI. Right, so I need to find the coefficient for this one, right? This is a cross-section view, okay? So how to do that? First, I need to find span length, okay? I have this span length, but this is not clear span. I need to find my clear span. So I need to find distance between the edge to edge. Okay, so this span is right here, okay, equal to what? Equal to 13 feet minus half of the width of the beam, okay? So that is 12.5 feet, right? 12.5 feet, that's the span length. So the span length of here, which is adjacent, right? So this is 1, this is 2, different, right? So this is 1, 2 equal to 15 minus half of the width. So this is 14.5. Okay, and again, this is another one, so let's call it 3, and 3 equal to 13 feet minus half of that, and this is 12.5 again, 12.5 feet. Okay, so per ACI, right? Per ACI, if I go back to the figure, I need to find
Hey,
out the
Bob.
moment. Yes, sir.
Wouldn't the span length be? Wouldn't you subtract 6 inches from both sides? So
Oh,
would-
yeah, you're right. So divided by 2. Yeah. God, okay. My head is not spinning. Thank you so much. Mistaken. So you're right. So this is, let me see, 12, right? This
Yep.
is 14, and this is 12. Good.
Yep. Thank you.
Okay. Thanks. Sorry about that. Yeah. Okay. So that is the. Let me just make sure I correct this. 2 part of it. Right. That's correct. 12 to, yes, that's correct. Okay, so that is the geometry. So how to determine the moment coefficient? How to determine the moment coefficient, right? So right now, this is what we're looking at. I want to even simplify more, right? I want to even simplify more. So I look at the structure, I say, look, equivalently, this looks like this. Okay. And then let me remove the end of it, make it, okay, this is fine. Okay, so equivalent looks like this. And I have a distance between this span right here, 12 feet, distance between this one here, 14 feet, 14 feet, and distance from this one here, 12 feet again. All right, so that's the span length. So how do I determine? I need to go back. Let me share another screen and show you the drawings, right? Show you the drawing. Hold on, where is it? Okay, so this is what ACI has, right? This is what ACI has. So this is on a textbook. This is in the textbook, and I also upload it. I also upload it. Okay. So now it says that. Okay, it says that I need to follow these tables, right? I need to follow these tables to find my moment coefficient, my moment coefficients. So explain to you again. What does it mean? What does it mean? So you see this number? Can you guys see my mouse? Anything? Can you guys see my mouse? Is it clear here?
Yeah.
Okay, good. So on the left side, you have this number 0, 1 over 24, 1 over 16. Okay, that means these are the number in front of this omega UL squared things, right? That is, these are number in front and omega u L square things at the end of this section right here, and it's negative. This is negative. Okay. And in the middle span, 1 over 11, 1 over 14, 1 over 14 is also number corresponding in front of the omega u L square thing. In the middle as a positive bending. Okay, and this negative thing is also here, negative thing, this is also here, plus positive is right in the middle span, and negative, negative. Now, there's a differences, right? Because you can see that there are three numbers here, one number here, one number here, one number. Why? Because these three numbers is dependent on the boundary conditions, okay? If it's discontinuous and unrestrained, that means it looks like this, unsupported, use 0 for the end. Okay. Correspondingly, if it is spandrel, which means it's integrated and like an L shape, use 1 over 24. If it's a column, which means it connected, interconnected, right? It is 1 over 16. 1 over 16. Now these 1 over 11, 1 over 14, 1 over the same thing. If it's discontinuous, unrestrained, is 1 over 11, right? Case 1 here. If it's spandrel, which means it's L shape like this, it is 1 over 14. If it's a column, means it's integrated and is 1 over 14. So this is the positive because in the middle span, all these at the joint are negative because they're at the connection. All right, so you see that the boundary condition, which means the end span condition, only influence, right? Only influence on the end and the middle span, doesn't have effect in the rest of it, to the rest of it. Of course, this is central line, means from the other end is symmetric, right? Symmetric at the end. Okay, so this is figure A, right? Means beams with more than 2 spans. And figure B, beams with 2 spans only, right? C, slab with spans not exceeding 10 feet. D, beams in which the sum of column stiffness exceed 8 times and the sum of beam stiffness each of the end of the plan, right? So we don't have to worry about the last one, which is the beam stiffness part. Okay, this is a little bit more advanced topic. All we have to remember is these A and B. Okay, A and B, they apply to both beams and slabs. Okay, both beam and slabs. And C, okay, which means slab with very short span length. Okay, very short span length. All right, so let's take a look, right? So given this is what we have, right? Given what this is what we have, what kind of coefficient we have? Okay, so today I'm a little bit lazy. I don't want to redraw it because I want you guys to see it, right? So these are the structure we obtained. We have LN1, LN2, LN3, etc. Okay, so let's take a look at the end of it. Now you see this right here at the end. It is spandrel, L-shaped, right? Spandrel, L-shaped, isn't it? L-shaped. So I go to this table. And find my spandrel, which is 1 over 24. 1 over 24. So I mark down here in my structure, it is 1 over 24 omega u ln squared, omega u ln squared. Okay, and this is negative 1 over 24 in front of it. Negative 1 over 24 in front of it. Continue back to my figure again to see this, and I'll upload this. You have it. And in the middle is second scenario, spandrel, which is conditioned like this in L shape. I have 1 over 14. 1 over 14. 1 over 14. So right here, take a look at that, and you mark down 1 over 14. Now, since this is middle span, okay, it's positive bending, so the positive sign, 1 over 14 omega u ln squared. Omega u ln squared. Then subsequently, this is negative 1 over 10. Okay, negative 1 over 10. See, can you guys see it? Negative 1 over 10 at the joint, which is negative here, and then negative 1 over 11, positive 16, negative 1 over 11, right? So go back here, just mark down, okay, 1 over 10 plus 1 over 16, and then this is negative 1 over 10, this is plus 14 because symmetric, right? And negative 24 again, symmetric, right? Now you notice that there's a negative 1 over 10 and there's a negative 1 over 11. I did not write down negative 1 over 11 simply because 1/10 is bigger than 1/11. So this dominates. I won't have one section cross the support. I won't have only one section cross the support. So I only mark down one value. Only mark down one value. These blue arrows are the supports. Okay, these blue arrows are the supports. Okay, so let me go back, right? Go back to show you in my drawing here, right? So this is how you pick out the moment coefficient. You just go back to the table, find out the boundary condition and find these numbers, right? Find these numbers and go back and mark them down on the structures. Mark them down on the structures. Okay, so let me walk you through again, right? Let me walk you through again. This is quite critical here. So follow that procedure I just showed. Okay, follow that procedure I just showed, right? So this is my current working documents, right? So I say, look, this right here, this value here, the support, blow them up and show that it is called spandrel. My pencil is defining me today again. Spandrel, right? L-shaped. So I will pick the coefficient on the table, right? Pick the coefficient on the table. So I suggest you draw similarly to my drawing here, so it'll be easier. Okay, so this will be support, and this will be support, and this will be support, and this will be support. And I use red to get my moment coefficient. So at this point, since it's spandrel, so here, let's call it A, and let's call it B, C, D, and let's call it B prime, which is middle span, C prime middle span, and D prime middle span. Okay. Okay, these are numbers and names. So from the coefficient table, right? I just showed earlier from the coefficient table, right? What you get here is MNA. So MNA, okay, MNA here is equal to 1/24, and don't forget it's minus, okay? Minus omega U ln squared. Okay, omega U ln squared. Okay, so number here is negative 1/24. Okay, and B, not N, sorry, MU. Okay, being foolish today. MU here applied. Okay, applied. Now MUB here, since it's positive 1/14, positive 1/14, so I say it's 1/14 omega U ln squared. Okay, at support B here, okay, and because on the left is negative 1/10, on the right is negative 1/11, I pick 1/10, kick out this lower value, so omega, sorry, MUB should be B prime, and this is positive, and then B is negative 1/10 omega U ln squared. Okay, now in the middle here is positive 1/16. So U C prime is positive 1/16 omega U ln squared. Okay, and then at support C here is negative 1/10. This is negative 1/10 again. Oops. Because it's symmetric, right? And this is positive 14 again. This is negative 1/24. So I just list down, right? So this is MUC equal to a negative 1/10 omega U ln squared, and MUD prime equal to a positive 14 omega U ln squared. Okay, and then MUD equal to a negative 1/24 MU ln squared. Okay, squared. Now it's not done yet, right? So I just blindly write ln, right? But they're not the same. Why? Because I have ln1, ln2, ln3. So I need to go back and make corrections. MUA is parent to this span right here, so it's 1. UB prime still this span here, 1. MUB still this span here, 1. Isn't it? No. No. Why? Because MB here has both contribution from the left span and contribution from the right span. So here for MUB, which is negative, I need to make a slight change here, okay? I need to make a slight change here. This is ln1 plus ln2 average, right? Divided by 2 average, then squared. then squared. Okay, be careful. Okay, now for C prime, see here, they only have one span, which is 2, so I'm fine. For MUC, same thing happens. Same thing happens. I have to take the average. I have to take the average. So ln2 plus ln3 now divided by 2, square it up. Okay. Now D prime, same thing, right? So let me just say this is the same thing. So it has this contribution, has this contribution. D prime is the same thing. So this is 3, this is 3. Okay. Folks, are we good? Are we good? Guys, are we good? I need to see if you guys have questions on this. This is very important. Any questions on this, guys? Anything? Are we good? Good understanding so far? Okay, so silent means good, I guess. All right, yes, any question? All right, didn't hear anything, probably just echo. All right, okay, so we assume we're good. And this is just a simple illustration of how we use it. How we use it, right? So it's pretty straightforward. We go to the table, and pick up the number and come back and apply it. As simple as that. It's not difficult, right? It's not difficult, right? But, okay, this simple analysis have problems. Simple analysis have restrictions, have limitations, okay? So what are the limitations? What are the limitations? All right, this is something I want to discuss with you, okay? There are very important limitations. Okay, so let's go back here. Okay. Let me continue, maybe. Let me just continue a little bit, okay? So I just want to use this example to show you how it's done, okay? Let's just continue. Say, okay, look, it looks very simple, straightforward. Very straightforward, right? So straightforward ACI approach, very efficient, straightforward, but normally, you know, this is 90% of the meat here, but there are limitations. There are limitations. Don't abuse it. Don't abuse it. If you use it everywhere, you're gonna in trouble, right? What are the limitations? Three limitations. Oh, well, let's extend it to 5, okay? Let's extend it to 5. 5 limitations, okay? 5 limitations. There are 3 major, but let me just say 3. 5 limitations. 5 limitations, okay? So number 1, use red, okay? Only applies when you have, only applies when you have 2 or more spans. If you have 2 spans or less, so you have 1 span, simply span, doesn't work, right? This is only for continuous. This is only for continuous. 2 more spans, right? 2 or more spans. Second, span lengths and approximately has to be equal to each other. Span lengths have to be equal to each other, approximately, have to be are approximately short, equal. Prefer to be the same, prefer the space, the same, right? And now, if they're not exactly the same, like we did here, right? I wouldn't have, and just use it. There's a 12 and there's 14. How dare you, Bob? You know, they're different. How can you use it? There's an exception, right? There is an exception. So the tolerance, the tolerance, yes, tolerance is 20%. Okay, 20%. Okay, that means the longer span is not more than 20% longer than the shorter. It's really a mouthful, but forgive me, it's not my language, okay? It's not my language, okay? Let me change a little bit, maybe greater. How about that? Sounds better. Okay, longer span of 2 adjacent means I have a support. You know, this is 2 span scenario. I have Ln1, I have Ln2, and say this is longer. So, right? So Ln2, right, divided by Ln1 cannot exceed than 1.2. Cannot exceed than 1.2. Okay. All right, so now that's the second limitation. Has to be equally spanned, okay? And the third one has to uniform distribution. So uniform loading, uniformly distributed load. Okay, have to be uniformly distributed. If it's concentrated load, no. So no to concentrated load. You have concentrated load, sorry, bro, out of luck. Gotta do the pattern loading. Gotta do the pattern loading, which is crazy. Okay, which is crazy. Now, these are the three most important because most of the cases are falling within this category. Actually, when I say most important, it means these are no-brainers, right? You can see this. This is always satisfied easily. Well, the other two are non-obvious. The other two are a little bit non-obvious. Okay, so the other two is live load. Live load cannot or does not, okay, exceed 3 times of dead load. 3 times of dead load. And be careful, okay? This is unfactored, okay? This is unfactored. Okay? Use mathematic, sorry, factored, unfactored. Use mathematic descriptions. Live load is smaller than equal than 3 dead load. Unfactored, okay? Unfactored. Okay? All right, okay, now here. The other thing is, in this case, there's a subcategory, okay? Subcategory. If, okay, if 1.4 dead load is factored, I wouldn't say this. I would say if 1.4 dead load is considered. Okay, why is this? Remember, we always say omega u to 1.2 dead load plus 1.6 live load, right? This is what we usually say, right? But instead of this, if you have 1.4 dead load, like this case, then cannot use moment coefficients. Cannot be used. Means you cannot use a simple analysis. Okay, all right, so why? Why? I mean, the live load does not exceed 3 times the dead load. It means, okay, I do not have too much live load, right? And you know why this is so important? Because remember the pattern loading. Remember the pattern loading back then here. Okay, if the live load exceed 3 times dead load, okay, then these pattern loading become useless. Becomes useless. Why? Because only the live load counts. Only the live load counts. And you really have to find out what exact moment you're applying to the beam to do the analysis. You cannot count on the moment coefficient analysis anymore. Okay. And the second, why the dead load 1.4 to be used, you cannot use a moment coefficient because when that scenario, again, your pattern loading does not apply. Your pattern loading does not apply. Okay, all right, so that's very important. There's constraints, right? And last but not least, very important, okay? Prismatic members. Prismatic members. You see, I draw earlier, I told you it's gonna be important. It is important. Why? Because you can only do like this. This is called prismatic, or like this. This is called prismatic. Okay, if you have something different, right? You have some weird shape like that, cannot use. Round or bowler like that, cannot use. Has to be prismatic members. Has to be prismatic members. Okay, and you say why so strict? Because we pre-calculate the stiffness assuming it's a prismatic shape, and there's a torsion coefficient for it. There's a torsion resistance for it. Okay, so it's a little bit advanced, but let's just leave it like that. Okay, leave it here. All right, so these are the important, okay, non-obvious ones. So I want you to pay attention to these ones. The previous ones easy to see, easy to spot. These ones are a little bit challenging, okay? Sometimes you forgot, ignore it, okay? Cannot. So there are 5 criterions and limitations, right? Means you check these 5 before even apply the moment coefficient. Okay, so now the impulse Bob, right, has done it already, right? Let's just go back to see if we're safe, right? To see if we're safe, I did it, you know, maybe I did it by mistake. So let's check. Let's check by these 5 criterions, by 5 criterions. Okay, so I didn't give you live load. I didn't give you dead load yet. right? I have no dead load and live load given. All right. So I'm just gonna give you, right? I'm just gonna give you, right? Let's say the live load equal to 150 pounds per square foot. Okay, 150 pounds per square foot, and the dead load is these iron factors is 75. Okay, 75. So let's check. Let's check 5 criterions, right? Let me just write down here. So number 1, what are the 5? What are the 5? First of all, 2 or more spans. 2 or more spans. How many spans we have? 3. So check. Pretty good, right? Second, the span length has to be approximately equal. What's the longest over the shortest ratio, right? So 14 over 12 is 7 over 6, roughly equal to 1.1 something. So let's just say 1.1, then close like that. So this is definitely smaller than 1.2. Okay, so check. 20%, remember? 20%. Okay, number 3. Oh, I'm running out of time. Let me just finish this, okay? Number 3, what are the limitations? Let me go back here, right? What are the limitations? Number 3 is what? Uniform distributed load, right? No concentrated load. So it is uniform. There's no concentrate, just dead load and live load, right? So uniform loading, check. Okay. Number 4, live load shall not exceed dead load than 3 times. That is almost 2, smaller than 3, check. Unfactored, okay? Unfactored. And number 5, prismatic member. Do I see anything wrong here? Nope, everything squared. So check. All right, so miraculously, we satisfy the requirement. Of course, I cheated, right? I made a problem that satisfies these requirements. But for you, in the exam, you have to check. You have to check to see if they satisfy. If they did not satisfy, we're in trouble. We're in trouble. Okay, we're in trouble. Now, I have one thing I haven't checked yet. One thing I haven't checked yet is 1.2, 1.4, right? Which one? Which one, right? So let's do it quickly. So omega u, if I use 1.2 dead plus 1.6 live, what I have 1.2 multiplied by 75 plus 1.6 multiplied by 150. And bear with just 1 minute. I want to finish this. This is 0.3, so 330 PSF. But if I say I use omega u to 1.4 dead load, that brings me up to 105 PSF. So this is to say that this is 1.2 omega u, this is 1.4 omega u, 1.2 dominant than 1.4. So check. If it's not, then still you cannot use it. Still cannot use it. You see, so the sacrifice or the price to pay if you want to use moment coefficient from ACI, which you really want, because doing the envelope thing is just crazy. So if you really want to use it, make sure you satisfy all these requirements. Okay, make sure you satisfy all these requirements. All right, thank you, folks. I think this is it for today. A good stop. You're welcome to say if any questions, or else I'll see you on Wednesday. Okay, I'll release the homework. You can start working on it one-way slab, but there's just last piece example I want to finish on Wednesday, which will be done with one-way slab completed. Okay. All right. Thank you, guys. See you guys later.